All right, I'm sorry, this won't count towards your time, but let's put on the microphone because it's being recorded. Yeah, so everyone else that goes for you too.
Right. Can you hear me? Yeah. Okay. So now, if you look at this operator has this capital Sk. Now, this capital Sk is basically a number operator. So let's say I have a spin state which is just plus minus states, and I act on the state by an operator. It gives me number. So the small number is just plus minus 1 depending on what spin it is, and I can take this state and do this kind of deformation. Now you see that I'm acting on Bs by exponential of minus LH0. H0 is the SYK Hamiltonian, and this gives me a very these are very special states in the sense these I won't have time to go into this, but these states have by itself in a pure SYK model have gravitational interpretation. So they have geometric interpretation, but they're interesting in many ways. For example, they look like Calabresi-Cardy states, which are models for post-quench states. And one more thing I can say is I'm going to make a claim is that for a particular L equals to L star, this BSL is the ground state of this model. And the heuristic argument for this is if I take B as infinity, it just projects this state into SYK ground state. And if I take B BS 0, it's the ground state of HM. So you could see that if these two numbers match, they'll give me factor of n by 2, and there's a minus sign, so it's the lowest state in this Hilbert space. And hence, it just interpolates between these two Hamiltonians, and for some value, there's a ground state. Now, I'm interested in computing transition amplitude, which I'm computing with both a complete Hamiltonian, and as Douglas has explained, the way I can do it is I can start from this Hamiltonian. I can write down an action, so there will be a kinetic term plus this term. I can integrate out the disorder. I can introduce the bilocals. After introducing the bilocals, I can project this action onto the effective low energy. So I can project this into low energy sector, where in SYK model we generally got just the Schwarzian theory, right? But now because my breaking term is not just the kinetic operator but also this operator, it gives me this extra term. Okay. Now one more important thing was that these numbers SKs and the numbers sitting inside BS have to match, and then only it happens. Otherwise you get a factor of cos theta, which is the angle between these two numbers. Then okay, so now for some time I want to discuss the gravitational interpretation of this Schwarzian mode. So you can understand this Schwarzian mode as this. So f of t is really so f can be considered as the bulk time, and t can be considered as the time along the boundary. So let's discuss some solutions. If I take a linear solution, this is how the boundary curve looks. So the green curve is the boundary curve, and you see these slices are the bulk time slices. So when t goes to infinity, f also goes to infinity here, right? So I can basically what I want to do is I want to as an n sitting here, I want to solve these equations at large n. At large n, I can make this transformation, and I get this action. And this is a very simple action. This is just a kinetic term with some potential, and it's this potential. And you can see that this potential has bound state and scattering states. So what generally happens is bound state corresponds to things that are ending here.
That's really the last.
Okay.
Or you can just leave it here. Hand it to the next person is the best strategy. And the next person is Adrian. There's also a laser pointer here if you want to use that, or this button.
Okay.
I'm not sure. It might. No, it doesn't. There.
Okay. Thank you.
Okay. Go ahead.
Hi, I'm Indranil. I want to start by thanking the organizers to give me an opportunity to present my work here. I work under Siraj Miniwala on matter-chance theories and their dualities. These dualities are successors of level rank dualities. Precise version of these dualities are finite level and rank exist due to work of Nathi and Ofer and many other people. Here I will be taking a different route. I will be taking the route through large N and finding evidence for these dualities. So I will start with critical bosons coupled with SU and Chern-Simons theories, and these theories are conjectured to be dual with regular fermions, fundamental fermions coupled with Chern-Simons theories. On the conformal manifold, we can study these theories, and operator data for single trace operators match on both sides. From the conformal manifold, we can turn on relevant and marginal deformations and can study 2 to 2 Onsel scattering matrices, high temperature partition functions on S2 cross S1, and these things match. But all these calculations that are done in large N are essentially done in the phase in which the scalar does not condense. So the question that I will be essentially asking here is what happens when the scalar condenses. So I will not get the time to explain the calculation, but I will be telling you about some results. As you have already guessed, the effective excitations in this phase is W and Z bosons. So I will start by 2-point function of W bosons. So gauge invariant data in 2-point function of W boson is the pole structure, and from the pole structure we find a non-trivial pole mass as a function of tube coupling and temperature and chemical potential, and this matches precisely with fermions under rules of duality. Next we consider 2-point function of Z bosons. 2-point function of Z boson contains a branch cut, and because of the presence of the branch cut, the Z bosons are not stable particles. They are stable only at the bosonic point. Further we consider calculation of free energy in these models, and they match with the fermions under suitable duality maps. Now I will be talking about regular bosons and their duals critical fermions. So in this theory, this is basic checks of duality works quite well at large N. Now I will be considering quantum effective action for the operator phi bar phi, and what we find is that this quantum effective potential is bounded from below only when marginal coupling takes a value in a finite interval. This interval is bounded from lower and upper both sides. So otherwise quantum effects makes the theory unstable, so you don't have stable vacua. Next I will be talking about deformations of n equal to 2 theories. So we deform n equal to 2 theories by giving the scalar some vacuum expectation value, and we ask the question, can we have any supersymmetric minima in which the expectation value for the scalar is still turned on, and we find there are, we compute the effective potential, quantum effective potential at large N and all order in tube coupling, and we find that there are new exact zero energy n equal to 1 minimas. So now the statement of presence of supersymmetry is not very accurate, because we don't have explicit construction of supersymmetry transformations in this phase, but nevertheless these are exact zero energy vacua that we find. Further we find the phase structure of these deformed theories. Essentially we have 4 phases corresponding to the boson is Higgsed or not, and the fermion Higgsed or not. What I mean by fermion getting Higgsed is that when the dual theory corresponding to the fermion is Higgsed or not. So all total we have 4 phases, and we find a quite rich phase structure in this deformed theories, in n equal to 2 deformed theories. And in this phase diagram there are non-trivial phase boundaries. In particular there are points where 2 higher order phase boundaries intersect, and those points we conjecture that there will be new fixed points, but so in particular at those points we can argue that the pole mass for fundamental degrees of freedom are 0, but still that it might not be a conformal field 3, but we still conjecture the existence of these points, and that will be our point of future study. So to summarize, we considered Chern-Simons matter theories in Higgsed phase, and we considered their stability, the question of duality, and their phase structures. And here I will be telling you about some future directions, which is like studying the supersymmetric theory in Higgsed phase more carefully, and possibly computing the Witten index, and to see if we can see this different n equal to 1 minimas changing, now number of them is changing. So that will be an interesting future work, and thank you.
Maybe have one question if there is one. Okay. All right. So whoever's next, Jonathan. Yes, Jonathan.
Oh, okay.
Oh, is that? Oh, that's
No, it just came up small, that's all.
okay.
It must have been...
It's somehow rotated.
Right, exactly.
I think that's you and not this.
Yeah, no, I agree with that. That's fine. Okay. Hi, everyone. My name is Jonathan Harper. I'm from Brandeis University. And today I'd like to tell you about some ongoing work with my advisor, Matthew Hedrick, to try and describe entanglement and purification in terms of bit threads. So the first thing I'd like to do is define what both of those things are. So entanglement and purification is a well-defined entanglement measure, even for mixed states. And it's found by taking a state and purifying it, and then minimizing the entanglement entropy over all possible purifications. In the past 2 years, there's been a proposal for a holographic dual, which is found by first calculating the entanglement wedge and then finding the minimum entanglement wedge cross-section. Bit threads are a reformulation of the Ryu-Takinagi formula, which is found by applying convex duality to the minimization of the area. And what you find is you instead calculate the maximum flux of a divergenceless bounded vector field in the bulk. So here you can see that we have some flow lines which go out from A, cross the minimal surface, and then end on the complement of A. So in this construction, the minimal surface acts as a bottleneck, limiting the maximum amount of flow that's allowed through the manifold. So the main question we want to ask is how can we use this bit thread formalism to describe entanglement purification? So the main modification we need to make is the addition of an additional boundary term here, which explicitly forces the threads to remain inside the entanglement wedge. So here, because the threads are not allowed to pass out, they correctly find this minimal surface, which is the entanglement of purification. So there are many inequalities which relate entanglement purification to other quantities such as the entanglement entropy and the mutual information. So what I'd like to do next is just describe a simple proof for one of those inequalities, which is given here that the entanglement purification is bounded below by 1/2 the mutual information and is bounded above by the minimum of the entanglement entropy. So for the first half, it's always possible for us to explicitly construct a flow that will calculate the mutual information. And this is done by taking a sum of two flows, one which maximizes the flow through A and AB, and the other which maximizes through B and AB. So because there's an explicit construction which we can always do, it's always an allowed flow when maximizing, so it will always be in the feasible set of allowed flows. For the second inequality, we notice that these two programs are related to one another in that the only difference is the addition of this extra constraint. And we know that whenever we have a maximization problem and impose additional constraints, it's necessarily going to mean that that new program has a lower maximum. So that gives this second bound here. And what I would briefly like to mention now is there's a generalization of entanglement purification to when you have more than two boundary regions of interest. And this is the multipartite entanglement purification. So I don't have time today to describe it, but we also have a complete flow formulation for the multipartite entanglement purification. So as a brief teaser, here we have three boundary regions given in red, blue, and green. And this is one of the flows which helps to calculate this orange surface, which is the minimal surface which gives the multipartite entanglement purification. And if you look closely, what you'll notice is that there is actually flux on the boundary here, which is the boundary of the entanglement wedge. So in order to get the multipartite entanglement purification, you actually need one flow for each of these boundary regions, and then there's some constrained flux which is tying them all together. So if you're interested to come talk to me, I'd be happy to describe this formalism to you more. Thank you.
Do we have time for questions?
Yeah.
There's a lot of quantity for this question. And this pre-described the idea to
Sorry, can you speak up?
this question.
Oh, isn't that always saturated?
But it's also defined.
Well, I mean, holographically, isn't it always saturated?
Well, I guess they're proof.
I believe that it's the case that for holographically that quantity is always saturated, and it's saturated by this mutual information. So as a result, because that basically is just saying holographically, it has to be saturated because you can always find. Right. So what I'm saying is if I can find this flow which gives me the mutual information, then that will basically has to be the quantity you're talking about.
So did you prove this entanglement of purification equation with the cross-section or not?
Yes, yes. So you can explicitly start with the minimization, apply Lagrange duality, and get out this formula in both cases.
Okay, so you say it's true now.
Yes, it's true.
Okay. Great.
This is the formula for entanglement purification using bit threads.
Okay, great, thanks.
Yeah.
All right, next.
Yeah, and this is no one here.
All right, now we have Nat. Ready?
Yep.
All right.
Hello. Can you hear me? So my name is Nat Levine. I'm a second-year PhD student in Imperial College in London. And I'm talking today about a recent paper, which is a collaboration with my supervisor, Arkady Zeitlin, and our collaborator, Ben Hoare. So the basic question here is, which 2D sigma models are classically integrable? So it's quite a hard question. We actually don't really know how to solve this question. In general, if I give you a sigma model, it's characterized by a metric and a B field on the target space. You don't know how to decide whether or not you can construct a lax pair for the equations of motion. That's what it means to be classically integrable. But I can hear you all screaming at me that what we should do is look at the S matrix, right? Because we know that in the massive case, integrability is closely associated with special properties of the S matrix. So these properties are no particle production and factorization. However, this is a classically scale invariant theory. So these excitations xi are massless. And it brings us to the thorny issue of the massless 2D S matrix. So it's come up a couple of times already in Zamolodchikov's lectures. Basically, it's thought that this massless 2D S matrix is not well defined. It's not a good observable. And this is essentially because wave packets don't separate asymptotically in this case. So this is a problem. But if you're interested in tree-level physics, classical physics, you can actually define the S matrix in a kind of unambiguous way using the action. So you use the action evaluated on a classical solution of the equations of motion with special scattering boundary conditions. And this is a generating function for the tree-level S matrix. So okay, you do this, and what happens? Well, the funny kinematics of massless 2D do rear their head. So you find that in a generic subclass of tree-level diagrams, internal propagators go on shell. So this is a divergence, right? But it's not a true divergence in the sense that since every interaction here has two derivatives, you actually find on shell that each of these divergences gets compensated by a vanishing factor. So you get these kind of 0 over 0 factors. So that we're kind of calling them IR ambiguities as opposed to divergences. Because it kind of looks like these could be finite if you interpret them correctly. So the purpose of this paper was just to classify these ambiguities and to study like some of the most simple ways of resolving them. So one of these ways, which I'll talk about today, is what we call the massive regularization. So this just corresponds to deforming the Lagrangian by a mass term. This is a very natural thing to do. Now I have a massive theory. And you use the same mass for all the fields, because basically if you don't do that, then you find an order of limits ambiguity later on. So I compute the massive S matrix of massive excitations, and finally I take a massless limit. And in fact, this massless limit is well defined. It's a well-defined procedure. There's no problem in taking this limit. And the result is that there is no apparent link to integrability. So this massless S matrix has no apparent link to integrability, at least in the usual way. So one example, which I've written here, is the principal chiral model. This Lagrangian is built out of a group symmetry current J. And it's a group space, so it's a sigma model on a group space G. And we found non-zero 2 to 4 particle production amplitudes in this model. So this really goes against our intuition from integrability, that classically integrable models should have no particle production. At least in the massive case, that's our intuition. And we found similar particle production amplitudes in 2 to 3 amplitudes in a whole host of related integrable models. I'll just say now what these are. PCMQ denotes the principal chiral model deformed by a Vesumino term with coefficient Q. The Zakharov-Mikhailov model is a classical dual of the principal chiral model, just at the level of the equations of motion, not at the level of the action. And lastly, the non-abelian dual is the usual path integral dual. So this model has G cross G symmetry. And this is like dualizing in one of those factors of G. 30 seconds. Thanks. So just as an important sanity check, I'll just say that the Vestumino-Witten S matrix, that's PCMQ with Q equal to plus or minus 1, this critical model, is trivial as expected at 4 and 5 points in our prescription. And that's expected because of left and right movers decoupling here. So there's a kind of open question of whether integrability is it imposing any condition on these massless amplitudes? Is there some weaker condition in the massless case than in the massive case? I mean, you may say that this particle production is just a result of an artifact of our prescription. But it may also be that there is no prescription with no particle production. Thanks.
Quick question while we're changing? You can ask a question. Go ahead.
2 minutes.
Yeah, go ahead. 1 minute. 1 minute. 1 minute. And hand the microphone to the
Very
next
technical question. Very technical question. You, in order to define it, you added this quadratic term.
Yeah.
Suppose I add also x to the 6th term with m squared, another m squared, and now compute 2 to 4 amplitude. Is it going to be different from the
Can you
first
just
one,
show me
or-
the laser photo?
It may be different, yes.
All right.
Yeah.
Okay.
And actually, this is an interesting thing, because if you can do this,
Like
if
this.
you can find a
Okay,
generic way to
thanks.
do this while keeping the theory integrable, then you would have no particle production.
Right, right. I mean, maybe you could still adjust the potential in order to kill all this.
Yeah. Yeah, this is possible, yeah.
Okay, great. I think we should continue with more of Sasha's favorite formulas. So,
So hello everyone, my name is Tom Levy and I'm a PhD student at Tel Aviv University. So today I'm going to talk about a family of field theories known as higher dimensional Liouville field theories, and this is based on a work I did with my supervisor Yaron Oz and Aviar Aviv Moshe that appeared in these 2 papers. So our motivation comes from the original 2-dimensional Liouville CFT, which was introduced long ago in the context of non-critical string theory and has been studied extensively since then. So this theory provides a realization of 2D quantum gravity and is related to various other theories, for example, to 4-dimensional n equals 2 superconformal gauge theory by the AGT correspondence. So the higher dimensional Liouville CFT is a generalization of the 2-dimensional Liouville theory to any number of dimensions. It first appeared in a paper about a field theory description of turbulent fluid flow. Turbulent flow is described by the Navier-Stokes equations in the inviscid limit where the viscosity goes to 0. And in this limit, we can talk, So in this limit, the Navier-Stokes equation have a scale symmetry, which is spontaneously broken by introduction of non-zero energy dissipation. So in the field theory description of turbulence, we can think of a Nambu-Goldstone boson that arises from this spontaneous symmetry breaking of the scaling. And the Liouville field is exactly this Nambu-Goldstone boson. So this is the action for higher dimensional Liouville CFT. Phi is the Liouville field, and it has a kinetic term, a background charge term, and an exponential interaction. The dimensionless parameters in this section are the background charge, the cosmological constant, and B that appears in the exponent. So the 2 objects that appear in this section are PG, the GGMS operators, which is a covariant generalization, covariant with respect to Walters function of the Laplacian to the power d over 2. So this action contains higher derivatives. And QG is a scalar curvature invariant, which also transforms covariantly under Walters functions. If we combine this with phi being a linear dilaton, so it transforms linearly with respect to the Weyl factor, we find that this action is classically Weyl invariant. And the field equations that are derived from this action describes manifolds with a constant negative Q curvature. In the quantum theory, phi is a logarithmic 2-point function, and the primary conformal operators of this theory are known as vertex operators. These are exponents of phi. So these are operators of the form e to the power d times alpha times phi, where alpha is some parameter. Looking at the scaling dimension of these primary conformal operators, we find that our theory has a continuous spectrum of scaling dimensions. So in our papers, we also considered a supersymmetric generalization of this theory, specifically the four-dimensional n=1 Liouville superconformal field theory, where the Liouville superfield is now a chiral superfield, and these two guys, the GGMS operator and the Q curvature, are generalized to a curved superspace. So to summarize our main results in analyzing this theory, we analyzed the three-point function of vertex operator of the primary conformal operators of this theory, and we got a formula for the structure constants of the theory. So this is the formula for the structure constants. It generalizes the two-dimensional dose formula for the structure constants of the original Liouville theory. In this formula, alpha 1 to alpha 3 are the exponents that appear in the three vertex operators, which we consider the three-point function of. And the epsilon BD is some special function related to the double gamma function. So this gives us all the structure constants of the theory, and this is a major step towards a complete bootstrap solution of these CFT. We also analyzed the Weyl and super Weyl anomalies of this theory, and for the supersymmetric extension of the theory, we proved the non-normalization theorem for the background charge Q. So this is it. Thank you.
We have time for a question.
Hi.
So, can you generalize in 6 dimensions?
6 dimensions, 8 dimensions, any even dimension. In the odd dimension, in the odd dimensions, I have a problem where the Laplacian to the power d/2 is a non-local operator. So the theory becomes non-local. But in any in any even dimension, I can generalize it.
But is it really a CFT? I mean, usually we said we don't know any CFTs in greater than 6 dimensions.
So it is non-unitary, so I don't... Yeah, so it's problematic in its own way, but...
Okay. All right, thanks.
Yeah.
Hi, so I'm David Tennyson, and I'm a third-year PhD student at Imperial College London. And I'm going to be telling you about some work I've been doing recently with my supervisor, Dan Waldron, and our collaborators, Anthony Ashmore and Charles Strickland Constable. And this will be coming out in a paper very soon. So what we're interested in is understanding the geometry of completely general compactifications of 10 or 11 dimensional supergravity down to 4 dimensions, and also understanding the moduli space of these structures. So when you compactify, you take your 10 or 11 dimensional theory, and you make an ansatz for the manifold, which for us is some 4-dimensional Minkowski external space and some usually compact internal manifold. And the geometry of that manifold can really affect the physics that you see on the 4D space. So for certain geometries, we'll be able to get preserved n=1 supersymmetry. So in our paper, we discuss lots and lots of properties of not just this, but the moduli space. And we give, for example, the Kähler structure of the moduli space. But today I'm just going to talk about the sort of infinitesimal deformations or the infinitesimal moduli of this space. So why might you be interested in this property? Well, the infinitesimal moduli essentially gives you the dimension of the moduli space. And this gives you the number of massless chiral fields in the effective 4D theory. Also, if you're able to understand sort of finite deformations, not just infinitesimal ones, you might be able to build a topological theory out of what's called an AKS-Z construction. And you might see this as a sort of first step along that process. So how do we analyze this problem? So we use a geometric technique called generalized geometry, and I don't have time to go through the mathematical details here. So if you're interested, you can come and talk to me about it later. But it's been known that if you want n=1 supersymmetry on the lower dimensional theory, your internal manifold needs what's called an integrable SU7 structure. And we have shown that this is equivalent to having some 7-dimensional subbundle, which we've called L, inside the generalized tangent bundle E. And the integrability condition is just the fact that it's involutive under some generalized Lie bracket. And this generalized Lie bracket is really just the Lie bracket on vectors plus some exterior derivatives on forms. And there's also an extra condition, which is a moment map condition vanishing. But I won't go through that here because it's not important to our discussion. So the picture you should really have in mind is of complex structures. So if you understand what complex structures are like, it gives you a pretty good intuition of what's going on here. So we kind of follow what Kadar and Spencer do in their deformations of complex structures, and we take a linear deformation. So we deform this L by some A in what's called the adjoint bundle, and this is just a vector bundle where each of the fibers are in an E7 algebra, and you quotient it by this P, which is just some parabolic subalgebra which preserves L. And we find if we impose this integrability condition, and you've just worked a linear order in A, this translates into some differential condition on A, which I've written d1 of A as 0. But we also have trivial deformations, and these are generated by diffeomorphisms and gauge transformations of your supergravity theory. And again, if you work through the algebra, then we find that trivial deformations are just given by some other differential acting on a generalized vector. So A is d2 of V. So we want to classify all closed A up to exact A. And this is precisely a problem in cohomology. So what we'll find is a vector space, and this vector space is pretty much the tangent space to your moduli space, up to some technicalities. And what we wanted to do is we wanted to analyze this problem in general, but that turned out to be quite hard. But what we have been able to do is take very specific examples, which are quite generic, and find all the moduli there. So a classic example is a G2 compactification of 11 dimensions. This is essentially the generalization of Calabi-Yau compactifications to 7 dimensions. And we find that all the moduli are just given by the third cohomology group of the de Rham differential. And this you might expect since a G2 manifold is given by a closed 3 form. We also found for GMPT solutions, which are compactifications of type 2, that we get these are the moduli. And I'm not going to go through what these cohomology groups are, but if you know generalized complex structures at all, you might understand some of the symbols I've written down here. So the point is that what we found is a completely general way of describing the geometry of any compactification. And given your favorite compactification, you can find exactly what the moduli are of these theories. I should also say that these moduli are both completely unobstructed. So they are actually 100% the tangent space of the moduli space at that point. Thanks very much.
Hi, I am Subhajit. I am a postdoctoral fellow in the Hebrew University, and my talk will be based on this paper written in collaboration with Barak Kohl, who is my postdoctoral mentor. So I will be talking about symmetries of Feynman diagram method, which is a new general method to evaluate Feynman integral associated with the Feynman diagram. Which, so this is a new general method which reduces the computation of a Feynman integral through the line integral over simpler diagrams. So by simpler diagrams I mean where one propagator is contracted. So this method also exposes a novel group associated with the diagram which depends on the graph topology, the Feynman, the diagram topology, and acts in the parameter space. So in this method we see that a Feynman integral denoted by I satisfies a set of partial differential equations which is sourced by the simpler diagrams. By simpler diagrams I mean if you have a diagram, if you shrink one propagator, it is sourced by that. So the general idea will be integrate this set of partial differential equations through the line integral. So and in some particular locus of the parameter space, by the parameter I mean if you have a Feynman diagram, there will be mass running in the propagators and also there will be kinematical invariance. So the Feynman integral will be function of those things. So in some particular locus of the parameter space where the parameters satisfy a particular constraint, it can be shown that the set of partial differential equations can be reduced to algebraic equations where the answer for the Feynman integral is not even a line integral, it is just given by a linear combination of the simpler diagrams. So it is an algebraic solution. So in particular I have worked with the diagram which is known as kite diagram in the literature, and I have considered the most general case where all the masses are different, and we have shown that in a particular locus where a cubic polynomial built out of the parameters which the diagram depends on is 0, then it can be expressed by just the linear combination of the diagram. Linear combination of the sources. So this is the central result where this particular cubic polynomial is known in literature as Bykov polynomial, which is nothing but the volume square of the tetrahedron. So, if you just join these two lines, this vacuum closure of this is the tetrahedron, and the B3 is actually the volume of the dual tetrahedron where face and vertices are interchanged. So, in this particular locus we have extracted the answer of these Feynman diagrams in terms of the simple diagrams. So, for this diagram the sources will be, if you shrink this parameter, this will be just a figure 8 diagram, and if you contract one of these 4 propagators, it will be a propagator-Seagal diagram. So, the central result is the kite integral with all possible mass excitations is a linear combination of propagator-Seagal and figure 8 diagrams at this particular locus. So, thank you. Yes. Any Feynman diagram, you can consider fermions, boson, and anything. Exactly. Yeah, it's general.
All right, let's just keep going. Get a little time. Other questions? All right, thanks. So, Ardia. Do you need the laser?
No, but can I put it here?
Oh, yeah, sure.
Yes. Hi, I'm Avia and I'm a PhD student of Professor Yaron Oz from Tel Aviv University. I will speak about supersymmetric quantum critical points in Lifshitz field theories. This work has been done together with Igal Arav and Professor Yaron Oz. So first, what is Lifshitz scaling symmetry? Lifshitz scaling symmetry is an anisotropic scaling symmetry in which time and space scale differently. So as you can see, t goes to lambda to the zt and xi goes to lambda xi, where z is the dynamical critical exponent which measures the anisotropy between space and time. In general, in these models, boost symmetry is broken, but for example, for z equals 1, the symmetry can be enhanced to the full relativistic conformal group. In nature, Lifshitz scaling shows up in some systems of condensed matter which exhibit quantum criticality. These are systems such as heavy fermion compounds and other materials such as high-TC superconductors, which have a strange metallic phase. In this phase, some quantities exhibit universal behavior, for example, a resistivity which is linear in the temperature, and this strange behavior is believed to be the consequence of quantum criticality. Now, at the quantum critical area, there is a Lifshitz scaling symmetry, and this is because the characteristic energy scale of the system diverges as the z power of the inverse correlation length, which exactly implies Lifshitz scaling invariance. Now, a natural question which arises in the context of Lifshitz field theories is whether one can construct supersymmetric extensions. Specifically, our main goal was to test the implications of holomorphicity in supersymmetric Lifshitz field theories. We focused on cases with Lifshitz scaling z equals 2, and the main outcomes are the following. So, we constructed a family of models with z equals 2 that contain 4 real supercharges which satisfy an algebra that closes only on the Hamiltonian of the system. These models contain a Keller term and a superpotential term. The superpotential is a holomorphic function of the chiral superfield phi, but in these models the chiral superfield is chiral with respect to a generalized superderivative that contains only temporal derivatives, not special ones. Also, it is important to mention that the dependence in the special derivatives in these models comes from the holomorphic superpotential and not from the Keller term as in the relativistic model. The superpotentials always contain a term which goes like G phi Laplacian phi, where Laplacian is a spatial Laplacian, and the G is called the relative strength of kinetic term. Second, we prove the existence of non-renormalization properties in a way which resembles the relativistic model in 3+1 dimensions. The holomorphic superpotential does not receive any quantum corrections. And third, and most interestingly, we found that these models, for various choices of spacetime dimensions and of marginal supersymmetric interactions, they realize a line of quantum critical points in which the system possesses an exact Lifshitz scaling symmetry, with a dynamical critical exponent that depends on the coupling constant. It is given by this relation, z equals 2 plus 2 gamma, where gamma is the anomalous dimension of the chiral superfield. But the system has an exact Lifshitz scaling symmetry. It is important to mention that this conclusion is based on the study of the RG equations and the symmetries of the theory alone. It is not based on any perturbative arguments. Therefore, it applies to the strong coupling limit as well. There are 3 such marginal cases of an exact Lifshitz scaling symmetry. We have n equals 3 in 6 plus 1 dimensions, n equals 4 in 4 plus 1 dimensions, and n equals 6 in 3 plus 1 dimensions, where n is the power of the chiral superfield in the supersymmetric interaction. It goes like fn phi to the power of n. So we've calculated perturbatively the sign of the gamma, the anomalous dimension, in all 3 cases, and we found that for the first non-trivial order, it has a positive sign, but we don't know whether this conclusion continues to hold for higher orders or for non-perturbative effects as well. Thank you.
All right, so we have time for a question. Yeah.
I didn't hear you. In 2 plus 1 dimensions, you have an infinite set of interactions that you can add because the scalar field is dimensionless under this equals to scaling transformation. But the non-renormalization, it continues to hold, the non-renormalization theorems. But the theory is not classically marginal because the scalar field is dimensionless. So you have to add either a derivative interaction or a coupling constant with dimensions. And that is not marginal, of course.
Hello, I'm Hongbin Chen from Johns Hopkins University. So I'm going to talk about Borg reconstruction and the black hole information paradox in the context of ADS3 CFT2. So the idea is to use 2D CFTs to understand steady quantum gravity in ADS at finite central charge. So the black hole information paradox can be already studied on the CFT side by computing CFT correlation functions. For example, you can compute the heavy light 4-point function, where the heavy operators are dual to BTC black holes, and the light operators act as a probe to probe the black hole geometry. But eventually, if we want to really resolve the black hole information paradox in ADS CFT, then we need to know what's happening near the black hole horizon. So we need to construct a Borg operator in terms of CFT operators and use that operator to probe the black hole horizon. And we want to be able to do this at finite central charge because we want to really include the quantum gravitational effects. So it turns out that in ADS3 CFT2, this is possible to do by using the Virasolo symmetries of the 2D CFT. So we show in this paper that these conditions uniquely fix phi at finite central charge, and this includes all the gravitational interactions. And if you solve these equations, you will find that phi is it can be written as a sum over CFT primary operator and all its Virasolo descendants and primary and global descendants. So using this definition, we can compute correlation functions of this Borg operator with other operators. And this is a CFT calculation, and the result of this CFT calculation agree with the Borg calculation using Witten diagrams. Here, I show you 2 examples, which is the phi OT 3-point function and also the phi 2-point function in the Borg at one loop. So now that we have this Borg operator, we can use it to explore various interesting Borg physics. For example, we computed this Borg 2-point function phi, and then we show that locality breaks down at a new length scale, L star, which is roughly 1 over c to the 1/4. And this length scale is between the Planck scale and the ADS radius. And this length scale also shows out as the string length scale in some ADS raised to string complexifications, but maybe that's just a coincidence. So going back to our original motivation, we want to study the black hole horizon. So now we use this definition of the Borg operator. We can compute this the solar bucket block of this four-point function, and then we can send this Borg operator to probe the black hole horizon. And in this paper, we developed several computational tools to compute these solar blocks, and we show that as you go near the black hole horizon, the difference between this exact safety calculation and the semi-classical gravity becomes larger and larger as you go near the horizon. But of course, the more interesting case is the Lorentzian black hole horizon case, especially the experience of an infalling observer, which is what we are currently investigating. So stay tuned. Thank you.
So we have time for questions?
Can you explain the breaking down of locality? What do you mean by that exactly?
So this CFT operator, this Borg operator phi is a scalar operator, a real scalar operator, and then we compute this phi two-point function, and then we found that when you send this distance to this scale, then the two-point function develops imaginary cut, which violates causality.
So let me also ask, so I'm not sure quite what you mean by exact here. So I would have thought, oh, in general mixes with other operators besides the stress tensor. So what do you mean exact?
We call this the photo field, which means that we only include the gravitational interaction. So by exact, I mean this exact in case of C. But of course, if you want to consider the full Borg field, then you need to include other kind of interactions.
Yeah. Okay. Thanks. All right. Okay, so now I have Upamanyu, so are you ready?
Shalom, I would first like to thank the organizers for giving me this opportunity. I am a third year student in TIFR. This is about work done in collaboration with my advisor Sandeep Trivedi and Ronak Soni, who was a fellow student. My job is easier now thanks to Daniel, who has told you that the lack of tensor product decomposition of a Hilbert space in gauge theory is related to the presence of a non-trivial center in the algebra of observables. However, the Hilbert space can still be written as a direct sum of tensor product terms, where the sum runs over superselection sectors. And in the extended Hilbert space definition of entanglement entropy, in which we trace over not only the physical states but also non-gauge invariant states, we get a sensible definition. And there are three terms. So the first term is a classical term which occurs for all theories, including abelian and non-abelian. The second term occurs only for non-abelian theories, and the third term is a quantum term. The essential difference between these terms lies in the fact that the classical terms are not extractable, while the quantum term is extractable from the point of view of local operations and classical communication. And in this particular work, we have explored how the classical term contributes to quantities such as relative entropy or mutual information. So as a very simple example, in 3+1 dimensional free Maxwell theory, we compute the two-point function of the normal component of the electric field on the codimension 2 surface, which is here z equals 0. And we find that it has a log divergence, and there's a scalar Laplacian multiplying it. What it leads to is the conclusion that the probability distribution, the classical probability distribution is dominated by high momentum modes close to the entangling surface. And as a consequence, the classical term drops out of quantities such as mutual information for disjoint regions A and B, as well as from relative entropy for states which have finite energy excitations about the vacuum. We have generalized this story for non-abelian theories. In SU and Yang-Mills theories, for example, we see a much stronger than logarithmic divergence, which is a power law. And the logarithmic divergence turns out to be a generic feature for p-form theories in any arbitrary dimensions, which are abelian. And we also find the Laplacian for P minus 1 form gauge theory on the codimension 2 entangling surface, which manifests here as a scalar Laplacian on the boundary. And now I'm coming to part which Nathi has described very well, which is duality, and we describe, sort of explore how the algebra of observables map into one another under electric magnetic duality. So it turns out that the conventional definition of magnetic center in the gauge theory side maps to the so-called electric center for general P-form theory in any arbitrary number of dimensions, with the addition of only a few operators, which I'll explain in a moment. So as a concrete example, we consider here 2 plus 1 dimensional theory in which Maxwell is dual to a scalar. This is the Maxwell lattice, this is the scalar lattice. We consider a region in the Maxwell theory which is this, and the region in the scalar lattice which is this. The Wilson loop in the Maxwell theory gets mapped to the momentum pi in the scalar theory, and the electric link operator in the Maxwell theory gets mapped to the difference of the scalar operators here. Although on the two sides of duality in the region R and the dual region R tilde, the operator content is not the same. In fact, the scalar theory has an extra operator which we call, let's say, sum over phi. It turns out that the entanglement spectrum across the two sides of duality are the same because of a very nice reason, that the reduced density matrix in the scalar theory is block diagonal in the momentum basis, and the addition of this extra operator does not change the reduced density matrix. So the entanglement spectrum agrees between two sides of the duality. However, this is true in general for d minus 1 form theories in d plus 1 dimensions, and this conclusion does not immediately generalize to higher dimension for higher form theories. For example, in 3 plus 1D Maxwell theory, which is dual to another Maxwell theory, if you consider the original lattice to be this lattice, and if you consider the dual lattice, it turns out that in comparison to the magnetic center, in the electric center you get certain additional operators. However, these additional operators do not contribute to UV safe quantities like relative entropy or mutual information in the continuum limit. And I am done. Thank you very much. Please ask me any questions if you have.
All right, let's go at the next speaker. We can have a question while we're setting up. Hand it to the next person.
Okay.
All right, you ready?
Okay.
Okay, so we have Kobayashi-san.
First, I'd like to thank the organizer for giving me the opportunity to talk here. I'm Nozomu Kobayashi from Kabri IPMU and University of Tokyo. I'm going to talk about my recent work about C theorem in defect CFT, which we propose a new conjecture. This talk is based on that paper collaborated with Yoshiki Sato, Tazuma Nishioka, and Kento Watanabe at the University of Tokyo. So let me start with my talk with motivation and review of the known result. So understanding RG dynamics is central to quantum field theories. And one of the most challenging problems is to prove the irreversibility of RG flows, which is guaranteed by the monotonically decreasing function, so-called C function. So if you can get such a C function, it counts the effective degree of freedom of the theory, and it also provides a powerful constraint on the RG flows, non-perturbatively. So the problem boils down to the existence of C function. Actually, there are a lot of works in this problem by several speakers at this school. And the first two-dimension case was done by Sasha, and the four-dimension case was proven by Adam and Zoha, and conjecture for three-dimension case was proposed by Igor and his collaborators. In summary, in even dimension, C function is associated with a type A central charge of conformal anomaly. And in odd dimension, so there is no conformal anomaly. So we use a sphere partition function as a C function. There are another conjecture which unify the even dimension case and odd dimension case and generalized to the continuous dimension, so-called generalized F theorem, using a sphere partition function. And another useful construction of C function is using entanglement entropy. Their construction is not totally equal, but at UV and IR fixed point CFT, we can map entanglement entropy for spherical region to sphere partition function. So they are connected. So let's move on to defector CFT case. So in this work, we compare the UV and IR fixed point CFT, and especially we consider D-dimensional CFT with P-dimensional planar defect. And as you can see, there are two possibilities for C function in defector CFT. One is defect free energy, which is response of partition function due to defect. And the other is defect entropy, which is increase of entanglement entropy by the defect. So the question is, which is true C function? Our main result is that we compute defect entropy for spherical region and relate it to the defect free energy, as shown. And they are not equal as the usual CFT, but different from second term. And this term is associated with non-vanishing of one-point function of stress energy tensor in defector CFT case. And this formula is a generalization of Yurkovitz and Murdasana's paper. Okay. So then we put a conjecture for C function such that not defect entropy, but defect free energy does not increase along defect energy flows. We check this conjecture for several CFTs, and we also find a non-trivial example in which defect free energy does not increase, but defect entropy does increase. And we also provide a holographic proof of our conjecture using problem model and ADS-B CFT correspondence. And our conjecture is consistent with and reduced to the known results such that G theorem for two-dimensional BCFT and B theorem for the CFTs with two-dimensional defect. Okay, that's all. Thank you.
We have time for a question. Any questions? I'll ask one. What's a defect CFT?
Okay, so we CFT with a conformal defect, which is a defect preserving maximal subgroup conformal group.
Like some domain wall that
like
conformal symmetry.
Like a boundary or interface or Wilson loop.
But it's not a boundary because there's things on both sides.
Oh yeah.
Is codimension 1?
No, any codimension. Yeah.
Okay. Thanks. All right. So Matt Hodel.
Yeah. So my name is Matt Hodel. This is work in progress with my collaborators at McGill, Alex Maloney, Sarah Harrison, and Omar Chama. So today I want to tell you something about pure gravity in ADS3 and its relation to the Euclidean Jakiv-Teitelbaum path integral. So as motivation, pure gravity in ADS3 is more or less exactly solvable. There's no local degrees of freedom. Another way to say that is there's no propagating gravitons. But it's still a non-trivial theory due to topological degrees of freedom. So in particular, we can recast it as an SL2R Chern-Simons theory. I'll come back to this asterisk if there's interest and time at the end. So one question you might ask is, can we account for the Bekenstein-Hawking entropy of a one-sided BTZ black hole by counting microstate geometries? I'll explain more what those are in a minute. So my claim is that we can do this calculation using random matrix theory. And in fact, it's the same calculation that Douglas Stanford will tell us about in his 4th lecture. I'm not going to explain random matrix theory right now. I'll leave that to Douglas, but I do want to try to motivate why it's the same calculation. Okay, so here in this diagram is a cartoon. It really is a cartoon. So the left-hand side is incorrect for reasons you can read about in a paper by Harlow and Jaffris, and that were explicitly checked in a paper by Kotler and Jensen. And the right-hand side is incorrect for reasons I'll tell you more about momentarily. Nevertheless, you can consider this single-sided BTC geometry in both the canonical and microcanonical ensemble. So the cartoon says in the canonical ensemble, we get it from looking at the two-sided BTC wormhole geometry and tracing over the left asymptotic region. And so we can, as usual, perform an inverse Laplace transformation to get to the microcanonical ensemble over here. And here the cartoon says that the microstates are described by gluing Riemann surfaces of arbitrary genus, compact Riemann surfaces of arbitrary genus behind the BTZ horizon. So you can estimate this number of states using the Born-Sommerfeld quantization rule as simply the volume of phase space divided by 2 pi h bar. That's h, or the original Planck's constant. So the phase space volume is calculated by this formula. So we look at the volume form of phase space given by the exponential of some symplectic form, omega, and we integrate it over the moduli space of genus G Riemann surfaces with exactly one boundary. That's the asymptotic boundary out here. And further, we want to sum over genus. So naively, this sum gives us a divergent answer, but motivated by this work of Schenker, Stanford, and Saad, which I forgot to mention before, that's work in progress, which calculates this Euclidean JT path integral. Motivated by this, we can include a weighting factor of e to the Euler characteristic of these Riemann surfaces, and this will regulate the divergence. So when doing this, you get an asymptotic series in the genus G, and this corresponds to the JT path integral, which you can calculate using random matrix theory, and this is what Douglas will explain to us in his lecture. You should probably ignore these expectation there. So if you include fluctuations in the boundary, the asymptotic boundary in ADS3 here, that corresponds in the JT story to the Schwarzian modes. So let me explain a little more. These pictures here are spatial slices of ADS3. So they're two-dimensional spaces. In the Jakiv-Teitelbaum interpretation, Euclidean path integral, they're two-dimensional Euclidean space times. And so that's why the pictures look the same, even though they're theories of gravity in different dimensions. Okay, so coming back to this question of can we account for the Bekenstein-Hawking entropy using these microstate geometries, the answer is not quite. In fact, not at all. We find an entropy that is, in fact, proportional to the Bekenstein-Hawking, the black hole area, but it's measured in ADS units, not Planck units, so that's pretty far off. But anyway, motivated by this work in progress by Schenker, Stanford, and Saad, we can instead consider the Euclidean ADS3 gravity path integral, the pure gravity path integral. So that would correspond to reintroducing the Euclidean time coordinate. So this path integral was already computed in the two-sided BTZ geometry in a recent paper by Kotler and Jensen. And our one current goal of ours is to modify this treatment to apply to these microstate geometries. And importantly, we want to include this asymptotic series in genus. And finally, dimensionally reducing along the Euclidean time direction should exactly reproduce the Jakiv-Teitelbaum answer. That's all. Thanks.
Any questions?
To be what? Oh yeah, the answer is that these aren't the microstates. There's just not enough of them. So we have to change the question we're trying to ask, and that's what I meant by trying to compute the Euclidean path integral.
Yeah, in Jakiv-Teitelbaum, that's more obvious because, as I mentioned, then there aren't any microstates. Okay, here we are. This is our last speaker. Ankoy, I guess.
Yeah, that's it.
All right, so go ahead.
All right, thanks for the brief introduction. Thank you also to the organizers for giving me a chance to talk and for making a very comprehensible school so far. So like you said, my name is Ankoy Chen. I'm a graduate student of Simoka Honryu at McGill University. And I'd like to talk about the work we published back in September about tree-level correlators at ADS5 cross S5 supergravity. So as mentioned by many speakers before today, n equals 4 super Yang Mills in 4 dimensions is dual to ADS5 cross S5 supergravity. And although it might be the most well-known duality, there are still surprisingly a lot of things that we don't quite understand. For example, the 4-point function for arbitrary single trace operators on the boundary isn't known for any, wasn't known for any mass dimension. And if you're trying to compute anything on the supergravity side, it's only been known since around August that these results for the 4-point function was computed. So what we would like to do is to understand, a precise question you can ask is to understand what happens to the set of operators that aren't protected by supersymmetry, which are called double trace operators. So if you scatter half BPS states on the boundary and you create particles during the scattering process, what is the anomalous dimension of these double trace operators? So to solve this, to answer this question, I'll resort to the bootstrap program. And so the bootstrap, for those who don't know, is to impose a set of consistency check to bootstrap correlation functions. And so for us, that means the set of constraints are as follows. The first one is superconformal symmetry, which just states that any correlator can be expanded in terms of conformal blocks and OP coefficients, here indicated by A. So for ADS5 cross SF5, because of the supersymmetric degrees of freedom, you have a factorization of the conformal blocks labeled by G and the S5 KK modes labeled by Z. The second condition that we impose is superconformal word identities. So basically, this just relates the different. Okay, so this relates to different components of the multiplet, and basically, the important part of the superconformal word identities is that you get, for any correlator, you get 3 components: the K, the F, and the product of G and Z. And the particularity of this decomposition is that for every of these 3 components, you have your own OP coefficient. And so the main tool that we'll use is the Lorentzian inversion formula, which basically for every correlators in the cross channel, you can reconstruct the S channel correlator by computing the double discontinuity. And so what you get from this are the OP coefficients over the poles that are located at the dimensions of the operators. And so I won't go through most of these results, but the most interesting part is that for at tree level, we were able to compute the anomalous dimension matrix for double trace operators, which matches a conjecture that was basically published a few months earlier. The interesting thing about this is that, as Dan mentioned today, you can probe a flat space limit by using ADS5 cross S5 supergravity. And so to do this, you basically exponentiate the anomalous dimension matrix, and this is roughly the scattering matrix in the flat space limit. And so what we observed is that if you exponentiate this anomalous dimension matrix and you compare it to the 4 graviton scattering in 10-dimension flat space, there's a eerie resemblance. And so based on this and other observations, we proposed that there could exist a 10-dimensional object with some conformal symmetry. And so what we showed is we constructed this object which depends on 10-dimensional cross ratios, and we showed that there is an operator that basically, when acted upon this G10, gives you all the tree-level correlators in ADS5 cross S5, including all the KK modes. So the first check, obviously, is to verify that this matches supergravity results, but also another check that you can do is to derive the melon space amplitude, which was proposed earlier, was conjectured earlier by Rastelli and Zhu. And using this result, we can also make a prediction of the 2-loop amplitude, 4-point function amplitude in ADS5 cross S5 using our 10-dimensional object. So thank you.
Time for questions. So when is this symmetry supposed to be true?
So we've only verified at tree level.
Do you think it extends further?
We're looking into that. We don't know for sure.
Or
Basically, I think Basso and others have, I think BC and Eric Perlmutter, they have a paper up where they're looking at alpha prime corrections to 4-point functions, and they said that they use our conjecture and they verified a little bit, at least for the stress tensor, that it holds. So it holds up to first order and alpha prime corrections for the stress tensor.
Is the point that this object G10 exists all the time in supergravity in 10 dimensions, not just in the decoupling limit? Or is it only when ADS5 cross S5 is applicable?
Well, we hope that it holds, but yeah, we have to verify for sure.
All right.
Right.
Thanks.
Thanks.
So that's the last slide I have. Dean, are you here? You're on the list here. Is Dean here? Okay. So then we're done, and so then I guess why don't we take like a 10 or 15 minute break, and then we'll start the tutorial with Douglas and myself. Let's say we'll start at 6, just so we can have a break. Okay.